All right, so in this video, we're going to talk about the chain rule in multivariable. So very similar to single variable calculus, when you have composition of functions, you apply the chain rule. That's the idea here. So we're looking for the derivative of w with respect to t. So we want to look at the change in w with respect to change in t. So now since there are variables x and y are also involved, so to find the derivative of w respect to t, we do need to draw a tree diagram. So here's how you're going to do a tree diagram to help you remember the formula. So we know that w is a function of x and x and y are both function of t. So you will start off with your w variable and then draw two paths for x and y because w depends on x and y. And now both x and y depends on t. So we have one branch out for each of these variables. So that's how you draw the tree diagram. So we now look for dw dt. So we want to see how this is changing as we change the t variable. Now, one way to remember this is to actually write out the derivatives or partial derivatives on the tree. So for example, if I want to find dw dt, well, we have to go along this path because that's where t is involved. And we also have to go along this path since that's where t is also involved, and we add them up. So on the first branch, this is the partial derivative of w respect to x. Now, the reason this is a partial derivative because here you have two branches, so you have two variables, you have to consider partial derivative rather the regular derivatives. And then the next path, we're going to write the derivative of x with respect to t. So that's the regular derivative since we only have one independent variable. Similarly, on this path, this is dw dt. Sorry, this would be partial of w respect to y. And then the next path, this is going to be the regular derivative, dy dt. So therefore, if you want to find the derivative of w with respect to t, this is simply this path right here plus the product of this path. So we're going to have partial derivative of w respect to x times dx dt plus, now the second path, we have the partial derivative of w respect to y times dy dt. So that is your formula if you have variable x and y, and then they both belongs on a single variable t. So let's take a look at it for this example. So for the first term, we want partial derivative of w, which is this function, respect to x. So you're going to treat y as a constant. So the derivative of w respect to x would be 2x times. Now for dx dt, we take the derivative of this with respect to t. So that will be derivative of cosine of t, that's negative sine of t, plus derivative of sine of t, that's cosine of t. So that's for all of these. Now the next term, we're going to take the partial derivative of w now respect to y. So now we're going to take the derivative of w respect to y. So here's our w. Take the partial derivative respect to y. So that will just be 2y. So we have 2y times. Now to take the derivative of y respect to t, so we look at this and differentiate respect to t. So you'll have derivative of cosine of t, that would be negative sine of t. And then minus derivative of sine of t, that's cosine of t. So there you have, that's your derivative, dw dt. Now, if you want, you can substitute x in terms of t and y in terms of t. So you have everything in terms of t. Now let's go ahead and evaluate since we're given a t value right here. That means we want to know what is dw dt at t equals 0. So we have dw dt evaluating at t equals 0. So we have 2 times x. Well, what is x when t is 0? So plug in 0 here. So we know sine of 0 is going to be 0. Cosine of 0 is 1. So we will have 2 times x. So that's 2 times 1. And then again, if you plug in 0 here, sine of 0 is 0. So we'll have 0 for that. But here cosine of 0 is 1. So we get 1. Now for the next term, we have 2 times y. So y is going to be what? Again, plug in the t value in place of y right here. So this is going to be 0, but cosine of 0 is 1. So we're going to get, again, that will be 2 times 1 times, now here, if I plug in t equals 0, for sine of t, we get 0, and cosine of 0 is 1. So that's going to give us negative 1. So this is going to be 2 minus 2, which will give us 0. So our dw dt is 0. Here we have another illustration of the chain rule. So we have w as a function of now x, y, and z, and x, y, z are both function of single variable t. So let's draw a tree diagram since we want to find the derivative of w respect to t. So first variable we're going to start with is w, and w depends on 3 variables. So you have 3 paths. We have x, y, and z. And all of these variable depends on one variable t. So we have t, t, and t. So w is indirectly connected to t. So we want to see what is the change in w with respect to t. So our formula is going to be dw dt is equal to, so when you take the derivative along this path, that's going to be a partial because w depends on 3 variables. So we'll have partial derivatives for all 3 paths to begin with. So we will have partial w respect to x, and this path will be partial w with respect to y, and this will be partial w respect to z. Now the next paths, so these 3, they're going to be just regular derivatives since now our x, y, and z depends on a single variable. So we just write dx dt. Here we have dy dt. Here we have dz dt. So now if I want dw dt, well, t is involved in all of these paths. So we want the product of this plus the product of this plus the product of that. So we're going to have 3 terms in our dw dt. We'll have partial w with respect to x times dx dt. So that's the first path we took, plus now the partial w with respect to y times dy dt. So that's the path right here, right in the middle. And then the last path, it's going to be partial of w respect to z of dz dt. So that's how you again rewrite the formula. So now let's find the derivative using this particular functions we're given. So dw, partial of w respect to x. So we're going to look at this right here and take its partial derivative respect to x. So we know that ln of a function, when you take the derivative of it, it's going to be 1 over that function. So this is 1 over everything inside of ln, that's x squared plus y squared plus z squared times the derivative of the inside. So that's going to be respect to x. So we just differentiate this because the rest are held as a constant. So this will be times 2x. So all of that is partial w respect to x times, now we're going to take the partial derivative of x, not partial, just regular derivative of x respect to t. So that's this one, differentiate that. We're going to get negative sine of t. All right, so that completes our first term right here. Now let's go to the second one. So now we have plus the derivative of w. So we're taking partial derivative of w respect to y. So here is y. So we're going to get 1 over everything inside of ln, that's x squared plus y squared plus z squared times the derivative inside, but that's a partial derivative. So we'll have respect to y, that's 2y times, now differentiate y respect to t, you'll get cosine of t. So that's our second term. Now the last one, we're going to differentiate respect to z. So first we take the partial derivative of w respect to z, so differentiate this. So you're going to have 2z over x squared plus y squared plus z squared times, now differentiate this respect to t. So that's the last part. So we're going to get 4 times the derivative of square root of t, that's 1 over 2 square root of t, and then we can simplify. All right, so we finished taking the derivative. And if you want, you can just simplify this further. But I hope you get the idea. Let me just rewrite one more step for you. So the first time we're going to get negative 2x sine of t all over x squared plus y squared plus z squared. The second term we're going to get plus 2y sine of t all over x squared plus y squared plus z squared. And the last one, here we can simplify a little bit. So the 4 and 2 will simplify to 2. So we'll have 2 times 2z, that's 4z over square root of t times x squared plus y squared plus z squared. So that is our derivative. I didn't rewrite x, y, z in terms of t, so if you want to do that, you can also do that. All right, so here's our last example illustrating chain rule. So now here you have w is equal to f of s cubed plus t squared. And we're also given f prime of x is equal to this function. And we want to find partial of w respect to t and partial of w respect to s. Now, to answer this problem, tree diagram will be very helpful. So we know w is a function of f, which is a function of s and t. Now, because of this statement, we're actually going to replace the input of f with x. So let's call this x. So let x be equal to s cubed plus t squared. So now let's try to draw the tree diagram. So we start off with w, which is a function of x, because f of s cubed plus t squared, we're replacing it with x. So then w depends on only one variable, which is x. We can draw this instead of branching two paths. And now x depends on two variables, s and t. So now if you partial derivative of w respect to t, let's do t first. Well, this is going to be, so we're going to go along this path. So this is the derivative of w. Since w is f of x, we can write that as df dx. So just a regular derivative because we have single variable. Now here, this is going to be partial of x respect to s. This is partial of x respect to t. dw dt, we just need this path right here. That's where the t variable is found. So we can write this. Now, again, if you want to replace w with f, feel free to do that. So this will give us the derivative of f respect to x times the partial of x respect to t. And derivative of respect to x, that's right here, it's given to us. That is e to the x. So we have e to the x times, now we take the partial of x respect to t. So s is a constant, that'll be 2t. Now feel free to plug in your x value into this x. So your final answer, you can also write this as 2t times e to the power of s cubed plus t squared. So that will be our partial derivative of w respect to t. So this will be partial of x respect to s. So again, the derivative of respect to x is given to us. That's right here. So that is going to be our term that goes here. And then partial of x respect to s now. So again, we take this expression, differentiate respect to s. That will be 3s squared. So that'll be our answer for dw ds. Or if you want, you can plug in x, which is s cubed plus t squared. So we have 3s squared e to the s cubed plus t squared. So that will be our partial derivative of w respect to s.